another 2, so 7. But for a diatomic molecule, we'll just take it, because we're always dealing with temperatures between 100 to 1,000, let's say, or 2,000, or even 3,000. We always have 5 halves. 5 degrees of freedom, so 5 halves. Okay. That's all. So what do we need to know? For monatomic, you would have 3 halves. For diatomic, you would have 5 halves. And let me just one thing. If you recall, so from this one, I can write delta E thermal will be 3 halves. I will write it in terms of this nRT. 3 halves and R delta T. Yeah. We remember this. And what did we say? Delta E thermal. How is it related to CV?
MCV delta T.
And CV delta T, right? So compare the 2 equations. What do you get? CV is what?
3 over 2R.
3 over 2R. Yeah, by comparing the two, right? Delta T, and is N. So the 3 halves R must be the CV. So that's CV. Monatomic or diatomic?
Monatomic.
Oh, R. Yeah, thank you. Is it monatomic?
Yeah.
Yes. If we had diatomic, we would have CV will equal to 5 halves R for diatomic. So what we really need to know is, it's usually given to you too. So we just need to know this. Now how about CP? How do I get CP?
5.
Yeah, CP is always CV plus R, right? We proved that in chapter 19, the relationship between CP and CV. Remember CP, whatever CP is, you add an R to it. So for monatomic, if you add an R, you will get 5 halves R for CP. And for this one, CP will be, you add an R to 5 halves, you get 3.5, which is 7 halves. 7 over 2. Okay, I think I said too much, but we didn't do an example. So I would like to do a couple of examples now. Okay, so, yeah, quiz time is almost there, and I forget. So I'll talk for about 10 more minutes. Yeah.
I have a quick question.
Yeah.
So when you were calculating for like kinetic energy, we're assuming that the molecule
Yeah, yeah. It's a balance. It's maybe not the. We assume too much. It turns out more complicated models will give you exactly the same result. Yeah, even if you assume more complicated assumptions, you end up with the same result, exactly the same.
like travel a very small distance.
Probably be off by a small factor, by just a factor. Otherwise, yeah. So that's why it's so easy to do this way. I think the book does it. Okay. Let us do the following. All right. Let us do the following. So suppose. All right.
That's what I'm doing.
So a monatomic gas at B equals to 0 degrees Celsius, and so find its thermal energy. So I mean, I should have said here. So you have 1 mole. You have 1 mole of monatomic gas. 1 mole of monatomic gas. Find its thermal energy. Its total thermal energy. How much thermal energy does it have? What should I do? I would find. I can find the kinetic energy per atom, and then multiplied by Avogadro's number, because I have 1 mole, right? To get the thermal energy, right? So I don't have the mass though, and I don't have the speed. What should I do to get the
Temperature?
Well, I can bypass the speed. As long as I have temperature, I can go back and get the speed. But, well, the thermal energy is just this, 3 halves NKT for 3 halves nRT. So that's what that's the thermal energy. So solution, E thermal is 3 halves and R T. Yeah. So, 3 halves. What is N again? Blue one?
Number of moles?
The number of moles, and we have one of them, right? 1 mole. R is always 8.31, right? And then the temperature should always be in Kelvin.
273.
So you add, yeah, 273. So, you can do this, and you get, oh wait.
3404.
Yeah, so about 3,400 joules. 3,400 joules. So that's how much energy there is. Okay, let me ask you a question, a conceptual question. How much heat is in this? Or does that question even make sense? Yeah.
Oh,
That's the thermal energy.
I mean,
Or how much work is in that gas?
3,400 joules, too?
Zero.
The thermal energy is 3,400 joules.
Oh, because work is your, right, yeah.
So work and heat are processes. Does not make sense for me to ask you how much work is in there. So work is done on it to change its thermal energy. Heat is added to change the thermal energy. But it doesn't make sense to ask how much heat is in it or how much work is in it. Yeah. Okay, that's the thermal energy. Now, let me do one more example for a, I think I will have enough time. So let's say I have a nitrogen, I will erase one board because we might need that. I have a nitrogen molecule at a certain temperature. I have a nitrogen gas. That's N2, right? Nitrogen gas is N2. And is at 20 degrees Celsius. 20 degrees Celsius. And then, so estimate its rotational frequency. Estimate its rotational frequency. I need to give you some more data. So it's nitrogen N2. Nitrogen N2 is a molecule. Here is M. And here is another M. Each of them is N, right? This is a nitrogen, this is nitrogen, right? And they're connected by a bond. And we're just going to treat it as a massless rod. Okay. It's at 20 degrees, so what did we say about vibrational energies? Do they come up? No. So for ordinary temperatures, they don't. So what can this molecule do? You can think of it as like a dumbbell. It can move, translate, in 3 directions. So how many degrees of freedom is that?
3.5.
3. And then it can rotate. It can rotate about its own axis. That's not a degree of freedom. It looks exactly the same. It can rotate this way about the z-axis, right? And it can rotate this way, or let's call this the y-axis. It can rotate about the y-axis. It can also rotate about the z-axis this way. Okay, so that's 2 additional degrees of freedom. So each degree of freedom is worth half kT, half kBT, each degree of freedom. Okay, so again, so I need to give you the length from here to here. L is 1.2 times 10 to the minus 10 meters. That's how far the 2 molecules are. And the question is, find its rotational frequency. So, rotational energy is what? If something is spinning about its own axis, like this. Remember from
1/2 pi omega squared.
Thank you. Yeah. The rotational energy, I put a little e here, not capital E, to say symbolize just for one molecule. So rotational energy is 1/2 I omega squared, where I is the moment of inertia. Remember that? Moment of inertia.
This is the one I think.
Not too many people like it. So I have 1/2. I need to replace it by something, and omega something else. They want the frequency, but remember omega is 2 pi times the frequency. Omega is 2 pi over the period, and the period is 1 over the period is the frequency, so it's 2 pi f. 2 pi times the frequency. Now what is I? They're rotating about here.
mR squared.
So it's mr squared for this one. The distance from here to here is r, and then mr squared for this one. So the moment of inertia would be mr squared plus another mr squared. So that's twice mr squared. But how is r related to L? R is L over 2. So I have 2m L over 2 squared, right? Because r is L over 2. And so this will be, when you square the 2 here, it becomes a 4th, but there is a 2 here, so you end up 1/2 little m times L squared. 1/2 m squared. So, 1/2 L squared. Okay. Yeah, questions on this one? 1/2 I omega squared. So the important is this rotational kinetic energy is 1/2 I omega squared. So let's simplify this. E rotational will be 1/2 times 1/2 is 1/4. But the 2 here gets squared, it becomes a 4. A 4 times 1/4. So all those 2's go away, right?
Yeah.
The 2's go away. And I end up with, again, the 2's go away, so I have m L squared. M L squared. You square the pi, you get pi squared. And you get f squared. This is rotational kinetic energy, right? About one axis. And we said the total energy, or the energy would be 5/2 NKT, or 5/2 KT, KBT for one molecule, 5/2 KBT, if you include all degrees of freedom. So this one is just one of the degrees of freedom, so it's worth the 1/2 KBT. So this will equal to 1/2 KB times the temperature.
What about N? What's it 1/2?
And
Isn't that in your formula?
so this N,
Yeah.
so if you have N molecules, but I'm considering just one molecule, so N, you can say N is 1.
Okay.
Yeah. I'm after F. So we need to solve for F. So divide by this and take the square root, so you get F equal to K B times T divided by, I have the 2, I have the M, the L squared, and the pi squared, and the square. So now is the time to substitute all the numbers. KB is 1.38 times 10 to the minus 23. The temperature is 20 degrees, so 293 K. 293 divided by 2. What's the mass? Is it the mass of the entire nitrogen molecule, or it's the mass per atom here?
Per atom?
Yeah, it's the mass of one atom, right? Because M and M, so it's just one atom. The mass of one atom of nitrogen, it has, 14 protons plus neutrons? So 14 times 1.66 times 10 to the minus 27 kilograms. L squared, L is 1.2 times 10 to the minus 10 squared, and then pi squared. Okay. Is this going to be a large or a small number? Very large or very small?
Very large.
Small.
Large.
Let's see. You got 10 to the minus 23 on top. You got 10 to the minus 27 on the bottom. And this is 10 to the minus 10 squared. 10 to the minus 10 squared is 10 to the minus 20. Times 10 to the minus 27, that's 10 to the minus 47. It goes up. It goes positive, 10 to the positive 47. And there is 10 to the minus 23. When you subtract them, you get 10 to the 24. And you square root it, you get about 10 to the 12. So that's a large number. So I said 10 to the 12. So it turns out to be about 7.8 times 10 to the 11.
That hurts.
And it's it's hertz, revolutions per second, or hertz, cycles per second, yes. If you want hertz. Okay. I think I will stop here. Next time we're going to continue. I hope to finish the whole chapter. I think we will. We won't
I need to reread everything.